So we have defined what it means for a map on a manifold to be smooth. But now we have a manifold with boundary. So what does it mean for the manifold to be smooth, at the boundary points? So one definition is that it should be smooth in a neighborhood, of the boundary. So let me write down the definition. A map from this manifold with boundary to M is smooth if it can be extended to a neighborhood in N cross R. Okay, so if it can be extended to a smooth map on a neighborhood is always open of N cross the closed interval in N cross R. Yeah. So, and a neighborhood is open, so you know what it means for a map to be smooth on an open set, right? So that's what it means for a map to be smooth on this manifold with boundary. And then I can define smooth homotopy. So two maps, F0, F1, from N to M are smoothly homotopic. If there exists a smooth map F from N cross the time interval 0, 1 to M such that at time 0, you have the first map, F0, and at time 1, you have the second map, F1, okay? So pictorially, it looks like this. Let's say this is N, and this is the time interval 0, 1, okay? So at time 0, this maps to well, it's F0, and it maps to something in M. And then at time 1, you have F1. So it maps N to something else in M. And then a homotopy really just means that as time goes from 0 to 1, you have maps. So, so you have, so the map F0 kind of evolves smoothly to F1, through like intermediate maps. Okay? Okay, so that's a picture of a homotopy. Yeah, so this is big F. Yeah. Now, a very simple example of a homotopy is the straight line homotopy. You see. Yeah. So let's say this is, F0x, and this is F1x. So the straight line homotopy is just a straight line from F0 to F1. So this point goes from here to here through time, and a straight line between 2 points is just given by the convex combination. So Ft of x is a convex linear combination of F0 and F1, and you want t equal to 0 to be this, so this should be 1 minus t times that, and then plus t times F1. So when t is 0, you get F0. When t is 1, this disappears and you get F1, okay? So this is the straight line homotopy. I mean, you can't always have the straight line homotopy, right? Because you need this line segment to be in your manifold, But if your manifold is convex, then you always have the straight line homotopy, okay? All right. Okay, so homotopy is a coarser equivalence relation, than say diffeomorphism. Okay. Yeah. So let me define what it means for two maps to be homotopy equivalent. Two maps are homotopy equivalent if they are inverse to each other up to homotopy. Okay. So let's make this definition. A map F from N to M is a homotopy equivalence if it has an inverse, but it doesn't have to be an exact inverse. It just has to be an inverse up to homotopy. So there is a G going the other way such that G composed with F, okay, which goes from N to N, is not the identity, but is homotopy equivalent to the identity on N. Oh, I use that symbol to mean smoothly homotopic. So over here, I guess I should write they are smoothly homotopic. Let me see. And so running out of space, but written F0 tilde F1. Okay? That means the two maps are smoothly homotopic. Okay? Yeah. So you need a map going in the opposite direction so that F composed with G and G composed with F are smoothly homotopic to the identity map. Okay? And then G is called the homotopy inverse, or G is a homotopy inverse of F. And the two spaces are said to be homotopy equivalent if there's a homotopy equivalence between them. So we say that in this case, M and N are homotopy equivalent, or have the same homotopy type. Okay. Now, this concept is important because it turns out that if two manifolds have the same homotopy type, then they have isomorphic de Rham cohomology. Okay? So when you are given a manifold, you try to find a simpler manifold with the same homotopy type. Okay? And then a manifold with the homotopy type of a point is called contractible. Okay. Okay, so let's look at an example of a homotopy equivalence. Okay. So the example is the puncture plane. The puncture plane. Now, let me draw the unit circle there. Okay. So it looks like, right, you can squeeze the puncture plane to the unit circle, right? Every point can be mapped to the unit circle. You have to remove the origin because, the origin cannot be mapped to the unit circle. So what is the formula? So I can define R, okay, let's see, that goes from the puncture plane to the unit circle by R of X. You just divide it by its length, right? Okay. So you've got this map. This is called a retraction. So a retraction is when you map from a bigger space to a subspace so that the subspace stays fixed, okay? So this is a retraction. But it's more than a retraction. Yeah, because, you can see that there's a homotopy from the identity to this retraction. So let I be the inclusion map. So I of X is just X. Okay. Okay. Now, okay. Then, well, you see that, let's see. So, R composed with I is going to go from the circle to the circle, and it will take X on the circle to X. Okay? So R composed with I is the identity. On the circle. Now, I composed with R goes from the puncture plane to the puncture plane. And it takes X to X over its length. That's not the identity, but it's homotopic to the identity. Okay? Via the straight line homotopy. Let me see. How do I get this to come down? Oh yeah, it's here. Okay. Let me see. Okay, I'm there. So the identity will take X to X, and then I compose R will take X to X over its length. And you see that there's a straight line connecting these 2 points. So you can define a straight line homotopy. Define F from R2 minus 0 cross 0, 1 to R2 minus 0 by F of xt is the straight line homotopy, so that at time 0, it's X, and at time 1, it's X over the length. Okay? Yeah, then F at time 0 is the identity map. Right. And then F at time 1 is X over its length, and that is I compose with R. I compose with R of X. And this is the identity of X. Okay. So I compose with R is not equal to the identity, but it's homotopic to the identity. Okay. So we have this. I compose with R. Is homotopic to the identity. And R composed with I is the identity, which is homotopic to itself. And this proves that R is the homotopy equivalence. Okay? And so the puncture plane has the homotopy type of S1. Okay? Yeah. You can generalize this example to other situations. So I'm going to make a definition. This R is called a retraction. So let A be a submanifold of M. Then a map R from M to A is a retraction if it leaves A fixed. Okay. So if when you restrict R to A, it's the identity on A. And restricting R to A means that R composed with the inclusion is the identity. And then a retraction is a deformation retraction if taking the composition in the other direction, you have something that's homotopic to the identity. Okay, let's see. Okay. So if I composed with R is homotopic to the identity on M. Okay? And we have the same conclusion as before. A deformation retraction is a homotopy equivalence. A deformation retraction so that M and A have the same homotopy type. Okay. And now, how does this relate to cohomology? It's because we have the homotopy axiom. Well, it's called an axiom instead of a proposition or a theorem because Eilenberg and Steenrod, they formulated a theory of cohomology based on a few properties. Okay, so like if you have well, a functor, that means like if you can associate, like a vector space, a group or a ring, to a topological space, and it satisfies a number of properties, then you have a cohomology theory, and then all the cohomology theories will have the same properties, if they have just those axioms, okay? And the homotopy axiom is one of the properties that a cohomology theory has to satisfy. So the homotopy axiom says very simply that homotopic maps induce the same map in cohomology. Okay. I mean, last week we talked about how any map induces a map in cohomology, right? So how does the map do that? So if F from N to M is a C infinity map of manifolds, can somebody tell me how it induces a map in cohomology? Like, you want to get a map from the cohomology of M to the cohomology of N, okay? And how do you do that? From last week. So a cohomology class is represented by a form, right? So, so let's say you have a form in M, and how do you get a form in N? Yeah, you just pull it back. So then you can pull back the form, and then you can define the map in cohomology by taking the cohomology class of the form to the cohomology class of the pullback. Okay? So that's how the induced map works. And we have agreed to write this also as F upper star. It's a bit confusing, but actually, usually it's okay, And so what the theorem says is that if F is homotopic to G, then F hatch is equal to G hatch, right? From the cohomology of N to the cohomology of N. That's the homotopy axiom. And we'll prove it next time. We'll just apply it this time. Let's see what the consequences are. Okay. So Well, the first consequence is that um, a homotopy equivalence induces an isomorphism. Huh? So, corollary. If F is homotopy equivalent to G, then oh, well, oh, no. Yeah, if it's homotopy equivalent to G, oh, yeah, then the induced map in cohomology is an isomorphism. Well, I guess I don't need to mention G. I just have to say that it's a homotopy equivalence. Okay, that means it's got a homotopy inverse. If F is a homotopy equivalence, then the induced map is an isomorphism. Well, what kind of isomorphism? It's certainly a linear isomorphism of vector spaces, but cohomology actually has a product structure given by the wedge product. So a cohomology has three operations. It has addition, scalar multiplication, and the wedge product. The wedge product makes it into a ring. Okay? What do you call a vector space that's also a ring? It's an algebra, yeah. So cohomology is actually an algebra. And F star, we know, preserves addition, scalar multiplication, and wedge product. So F star is an algebra homomorphism. If it's an isomorphism, then it is an algebra isomorphism. So the conclusion is that F star is an isomorphism of algebras. Okay? And this is easy to prove because since F is a homotopy equivalence, it has a homotopy inverse. Let G be a homotopy inverse of F. Okay, this means G composed with F is homotopic to the identity on N, and F composed with G is homotopic to the identity on M. Okay? And now you apply the homotopy axiom. Then you get G composed with F star is the identity on the cohomology of N. Yeah, I'm using F star for the induced map in cohomology now. Yeah, I wrote F patch there. But as I said, usually we write this also as F star. Okay? We write it as hatch only if it's necessary to distinguish the map on forms and the map on cohomology. Okay, so by the homotopy axiom, then you get this, and this is the same as F star composed with G star. And you have it in the other direction too. F composed with G star is the identity on the cohomology of M. And this is G star composed with F star. And that shows that F star is an isomorphism. Okay. That's F star on cohomology. It's a bijection. And because it's a algebra homomorphism, it is an algebra, because, yeah, it is an algebra homomorphism, it's an algebra isomorphism. Okay. And another corollary is that if M and N have the same homotopy type, then that means there's a homotopy equivalence between them, and that means there's an isomorphism between their cohomology. So you can say that if M and N have the same homotopy type, then they have isomorphic cohomology. And so now, because we know that the puncture plane has the homotopy type of a circle, so now we know the cohomology of the puncture plane. This should be an isomorphism, but I often write equality, you know? Yeah, so it's R in degree 0, 1, and 0 in degree greater than 0, okay? And suddenly, we now know the cohomology of a lot of spaces, okay? So for example, what is the cohomology of Rn? What is the homotopy type of Rn? Just a point, yeah, because if you have Rn, you know, there is a straight line homotopy to a point, right? You have a deformation retraction to a point, okay? So the cohomology of Rn is the cohomology of a point. And it's R in degree 0 and 0 in degree greater than 0. Oh no, I wrote something wrong and you didn't point it out. Here, the cohomology of S1 is 0 in degree greater than 1. You didn't notice that? That's terrible. Okay. Okay, so yeah, we have the cohomology Rn, and what else do we have? Yeah, okay, maybe that's good for now. Oh yeah, like how about the cohomology of a cylinder? See, okay. So when you have a cylinder, um, well, I mean, you see that it has the homotopy type of a circle, right? Because like, let's draw this circle here. And then you can deformation retract the cylinder to a circle using the straight line homotopy. Okay. So that's the cohomology of a circle. Um, although we know the cohomology of circle, usually that's not good enough. You know, you should also know the generators. Like, you know, the generator in degree 0 are, well, you know, any non-zero constant function, right? But what is a generator in degree 1 of the circle? So now, since we know that H1 of S1 is R, a generator is just any non-zero element. Any non-zero cohomology class, okay? Generators, they are elements that span, you know, the vector space, okay? So if you have just a non-zero cohomology class, it will be a generator. And what is it represented by? If you want to write down a generator, so what do you have to write down? Like what kind of object do you have to write down? I mean, would you write down a function or a number or what? You have to write down a one form, right? Yeah, a closed one form, but every one form on the circle is closed. So you just need to write down a one form, okay? But can the one, well, the one form has to be non-exact, right? Because if it's exact, then it would give you the zero cohomology class. Okay. Now, if a form is exact, how do you make sure that the form that you write down is not exact? So if omega is equal to d tau on S1 is a one form on S1, then what's the integral of omega? Yes, it's going to be 0 because you're integrating d tall. And then how do you see that this is 0? By somebody's theorem. By whose theorem? Stokes' theorem, yeah. So by Stokes' theorem, this is tall over the boundary of S1, okay? But S1 doesn't have a boundary. So the boundary of S1 is 0. It is the empty set. And, if you integrate over the empty set, you get 0, okay? So if you have an exact one form, its integral will be 0. And therefore, a generator is represented by any one form whose integral is not 0. Okay? And do you know of a one form whose integral is not 0 on the circle? Well, this one, minus y dx plus x dy. If you integrate this on the circle, and you use the usual parametrization, of the circle, xy is cos theta sine theta, where theta goes between 0 and 2 pi, then when you work it out, you'll see that it's just d theta. Okay? And you'll integrate that from 0 to 2 pi, so you will get 2 pi. Okay? Yeah, so this would be a generator. But usually, we like our generators to correspond to 1. Okay? So we'll divide it by 2 pi. So let omega be equal to minus y dx plus x dy over 2 pi, and that's d theta over 2 pi. Then the integral of omega over S1 will be 1, and this is the form we usually use as a generator, okay? So the class of omega is the preferred generator. Of H1 of S1. Okay, very good. Let's take a break and we will restart at 11:25. All right. So for the rest of the class, I want to calculate, as an example, the cohomology of a torus. Okay? Now, in the calculation, there's a step that's kind of tricky. And so I want to isolate it out and talk about it first. It concerns integrals on a cylinder. A cylinder is a manifold with boundary, and the boundary are 2 circles. Okay? Now, in doing integration, it's very important to get the orientation right, because if you have the wrong orientation, you'll get a minus sign, and then your answer might come out wrong. Okay, so I'm going to orient the cylinder like this, and it induces a boundary orientation, okay, on the boundary. Now on this circle, should the orientation be going to the right or to the left? Right or left? The boundary orientation. You want to volunteer? How many people say that it goes to the right? Raise your hand. How many people say that the boundary orientation goes to the left? It's very divided. All right. So the way boundary orientation works for a surface is that you just follow the arrow, okay? And this arrow, it goes like this. So down here, it should go like this. Down here, it goes to the right. How about up here on this circle? Does it go to the right or to the left? How many people say that it goes to the right? How many people say that it goes to the left? Most of you have no opinion. I just told you that you follow the arrow. So the arrow is going this way, right? So it has to go this way. That's the boundary orientation. Okay? And let me call this circle S1A and this circle S1B. Right? Now, okay. Normally, so like on the cylinder, I'm going to orient all the circles consistently. So this one is S1A, goes that way, and then it goes that way, goes that way, goes that way, S1B, okay? That's not the boundary orientation. That's just like the way I orient all the circles on the cylinder, okay? So actually, with this orientation, it's minus S1B, because S1B is the circle with the orientation going to the right. But in the boundary orientation, it has to go to the left, okay? So I'm going to call the cylinder C. Okay, and with circles oriented like that. And then the boundary of C is S1A minus S1B. Okay? The minus sign means the opposite orientation. Yeah, that's how you orient the boundary. And then suppose that omega is a closed one form on C. Okay, then the claim is that the integral of omega on S1A is equal to the integral of omega on S1B with these orientations. And the proof is Stokes theorem, because the integral of d omega on C is 0 since omega is closed. And by Stokes theorem, it's the integral omega over the boundary. And the boundary is S1A minus S1B. Okay, so that's the integral omega over S1A minus the integral of omega over S1B. Because when you reverse the orientation, the integral changes sign. And therefore, the integral on S1A and S1B are equal, okay, if they are oriented consistently. Right? Okay, and now let's compute the cohomology of a torus. Okay. Now a torus looks like this, and I'm going to use two open sets to cover it. So this is one open set. So U is this. Okay. And then V is the other side, but you know, you have to stick out a little bit so that there's an intersection. So V is this part. And then the intersection has two components that we call A and B. Okay. All right. So V that's U, that's V. And then the intersection looks like this. They're all cylinders. Okay. And now we write down the Mayer-Vittora sequence. So you have H2, and then let me see, about H1 here and H0 down here. Okay. And we fill in what we know. The torus is connected. So H0 is R. U and V are connected. So H0 is R plus R. And then V is connected. No, the intersection, oh God, the intersection is way over there. Okay. That's H0. And in H1, We don't know the H1 of the torus. H1 of U, that's a cylinder, so it's R plus R. Here there are two cylinders, so it's R plus R. And then in H2, you have 0 here. Okay. And this map is I star. This map is J star. This is I star. This is J star. This is in degree 0. This is in degree 1. Okay. And we know what this map is, right? It's just a restriction. So the constant function A goes to AA, and then J is the restriction of the difference. So BC restricts to BC, and you take the difference on each component. That's J star, okay? The really crucial map that we have to figure out is this one. If you can figure it out, then you can write down the kernel and the image, and then you can work out the cohomology. Okay? So what is that map? Okay. Okay, so we just look at where a generator goes. Now, let omega u be a generator of H1 of u. I will say the preferred generator, okay? That means it integrates to 1 on, yeah, you see, because U has the same homotopy type as a circle, right? Say S1U. So that omega U should integrate to 1 on this circle. And let's orient them, say this. And then here, this circle is S1A, and this one is S1B, and we orient them consistently, okay? Like that. Okay, so here is a cylinder. S1A and S1U are the boundaries of that cylinder. So I know that by what I have done before, I should have called it a lemma by previous work. I know that the integral of omega u on S1U is the integral of omega 1 u, no, just omega u on S1A. And it's the same as the integral omega u on S1B. And because I'm choosing the preferred generator, the integral is 1. Okay? So that means, yeah, omega u, it restricts to a form on one form on A, and because the integral on S1A is 1, it restricts to a generator. So thus, J1 star, it will take the generator, okay, to the generator on A and the generator on B. Okay? And similarly, it will take, if you pick a generator on V, that will be 0, 1. And it will also go to the generators on A and B. Okay? And so, what does it take AB to? Well, if it takes 1 to 1, 1, it will take A to AA. Okay? It will take B to BB. And then J star is the difference of the restriction. So it should go to what? On A, it should be what? B minus A. And so that is the map J star. Okay? And now we can calculate H2 of M because the exactness of the sequence says that H2 of M is the image of D1 star. And the image of D1 star is the domain over the kernel of D1 star. Okay, that's the first isomorphism theorem. And but the kernel of D1 star is the image of J1 star. That's exactness of the sequence. And J1 star is the map up there that maps to the diagonal. And so we know that the image is the diagonal, so it's one-dimensional. So I will continue here. And so you get R. Okay, that's H2. H2 is R. And now let's work out H1. So let's see, let's look at this exact sequence. Just a minute. Oh yeah, here. This is H1, right? So H1 of M, let me see. Oh, sorry about that. H1 of M over the kernel of I1 star is the image of I1 star. Okay, that's the first isomorphism theorem. And then the image of I1 star is the kernel of J1 star. Yeah, that's exactness. And where is my J1 star? J1 star is here. What is the kernel of this map? it's the diagonal again, because it's when B is equal to A, right? So the kernel is the set of AA. That's the diagonal, so it's R. That's the kernel of J1 star. And now I have to figure out the kernel of I1 star, okay? Now, the kernel of I1 star is the, by exactness, it's the image of this map, D0 star. Kernel of I1 star. Is the image of D0 star. And the image of D0 star is the, oh, just a minute. Yeah, image of D0 star. We have to do that again. So, gosh, where is my exact sequence? Right. The image of D0 star is the domain over its kernel. So it's R plus R over the kernel of D0 star. And then the kernel of D0 star is the image of the preceding map, J0 star. And that's, again, is the diagonal. So it's R, okay? The kernel of I1 star is R. And now we can write down H1 of M. So so we know that H1 of M over the kernel of I1 star is R. That's what we had before. But the kernel of I1 star, I have just determined to be R. So H1 of M over R is R. And that implies that H1 of M is R2. Okay? All right, so we have computed the cohomology of the torus. And in the homework, I ask you to compute the cohomology of the sphere, and you can use the same method. It's simpler. But next week, I will ask you to compute the cohomology of the projective plane. And you can use the same method, but it's a little bit trickier. Okay, so that's it for today.